Welcome back, everybody. Since I just got one of these labs just turned in here, I wanted to talk about them a little bit. This looks like a great one. Sydney has done a good job here. She's filled out completely the introduction here. It's surprising what you can put in there about what you're going to be doing, why you're going to be doing it, and so forth. I looked at some of them and I only saw like one line on the top. Well, when I grade that, I'm going to put -1 whole point out of 10 for not having any introduction whatsoever. I haven't looked at the rest of this, but on the other page you'll have your sample calculations. She's got a graph and so forth. And these are due either Monday or Wednesday, depending on when you come in. So for the air track lab, which we're doing now, I guess you folks will be coming in on Wednesday, is that true? So that's when you'll turn that one in. Okay, hopefully I'll have the other ones back to you by then. I'm starting to catch up and get into the groove of things and so on and so forth. And you'll be happy to know that the next lab that we'll be doing, I'll be handing out the lab items Monday and Wednesday as well, depending on when you come in. One change is going to be, I'm not going to call them lab quizzes anymore because they're not really a quiz. It's really a set of lab questions that you can do. Do them after you do the lab. It's a set of lab questions. And by the way, follow the instructions in the videos. If there are other things in the lab handout it says to do, you don't have to do those. You have to do what I outlined in the video. Okay, we're doing a little bit less for most of these because it's so difficult doing it online. So follow the instructions in the video as to about what things you should be doing in the video. Follow that, okay? That said, let's get into adding vectors. Adding vectors by the component method and finding components and then taking the components and finding the polar form of the vector is going to be such a fundamental thing in this course that we got to get a good foundation in. We've already talked about how you can add them graphically. There are two ways. There's the parallelogram method and then there's the head-to-tail method. But to get accurate results that are free of the inaccuracies that are inherent in graphing, we have to use algebra. And we talked about the x and y components of a vector, finding them, and let us pick it up there. The rule for adding vectors algebraically is quite simple. If a resulting vector is the sum of two vectors. We'll talk about the difference too. If you subtract two vectors, you negate the second vector and then add. If a resulting vector, that's what R is the sum of two vectors, then the x component of that vector is the sum of the x components of the two vectors, and the y component is the sum of the y components. If there are 10 vectors here, then you can say that you find the x component of all of those vectors, you add all of those vectors up, subtracting of course if a vector component happens to be negative, to get the resulting x component. Find all the y components and add them all up algebraically to get the y component of the result. Then, once you have the components of the vector, if you want it in polar form, we use the Pythagorean theorem and we say that the magnitude of that result, which can also be written as the absolute value of that vector, is the square root of the sum of the squares of the x and y components. And when you square a component, when you use the Pythagorean theorem, you never ever have a negative sign anywhere in here. When you square, if it's a negative component, when you square a negative number, you always get a positive number. You never subtract when you use the Pythagorean theorem. You always add. Because when you square any component, whether it's plus or minus, you always get a positive number. As far as the angle, you use trig and a diagram to get the direction. And I'll show you how to do this. This is my method, and it's the method I want you to use to get it. All right? This is best shown by doing an example, and I think the one that I wish to do here, because you get into this chapter and you're going, what the hell is going on? I think what I'm going to do is I'll do best example 3-3. All right, this is best shown. Example in the textbook 3-3. And what we're done here, we're told an airplane has 3 legs. Have you ever been on one of these puddle jumpers, these little teeny weeny planes where you have to... I remember when I was interviewing years ago, my first flight had mechanical problems, and I wound up riding these little tiny planes all the way, and I was sick by the time I finally got there. I was sick by the time I got there. And I went here, and then I went there, and then I finally got to there. So let us look at these. East 620 kilometers. East. The second vector, they call these D, D1, D2, and D3 in the book. It's easier to call them A, B, and C, because you just got to write one symbol. The second one is southeast 440 kilometers. Southeast 400, did I say 440? 440 kilometers. And this illustrates something else. The directions, southeast, northeast, northwest, southwest. That means they are at 45 degrees in between north and south axes. It means exactly, when you say southeast, you mean 45 degrees down. Not somewhere down here, you mean exactly 45 degrees. And when I say give me the magnitude and direction of the vector, I don't want some crummy description. I want a diagram showing that you know what that particular direction is. All right? And then the third leg of the trip, third leg, is 50 degrees south of west, 550 kilometers. 550 kilometers, 53 degrees, got to be careful here to get it right, south of west. All right, what is the resultant? What is the sum of these 3 vectors? Add those 3 vectors. The rule is you must draw a diagram for each one. You're going to have to draw 3 diagrams here. Because one of the difficulties you're going to have is determining the sign of the components. Class starts at 2 o'clock. All right. What you need to do is draw the first one. A is we draw an x and y axis, north and south, and it's 620 kilometers east. Now, what I'm going to do is I'm going to use east is plus and north is plus. So east is plus and north is plus. And this thing is pointing this way 620 kilometers. What you must learn is to look at the diagram and by inspection determine whether the components are positive or negative or possibly zero. By inspection. The method that I use here always involves using angles that are less than 90 degrees. If you're given an angle that is larger than 90 degrees, what you can do is use geometry and find an angle less than 90 degrees with respect to some other axis that you can use. My angles are always less than 90 degrees. You may have to do some intermediate work. But by inspection, we look at this. There's another rule. If a vector is parallel to a coordinate axis, the component of that vector on the other axis is automatically zero. If a vector is parallel to a particular coordinate axis, the other component is automatically zero. Well, looking at this, we see that AX and AY is 0 kilometers. By inspection, it has no north or south component. Just by looking at it, no math required. Furthermore, the other component is the magnitude of the vector with a possible negative sign. Now, since that's pointing in the positive x direction, is it positive or negative? It's plus. By inspection, it's plus. If a vector is along a particular coordinate axis, the component of the vector along that axis is either plus or minus times the magnitude. You have to look at it and decide. If it were pointed west, what would it be? It would be negative. So there are the x and y components of A. To add vectors, you must first find their components. Let's draw the second one. 440 kilometers southeast. Now, southeast means exactly 45 degrees down from east. This is 45 degrees. Could you draw this one as 45 degrees? Sure. 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 Now, lattice rule says this. Once you have figured it out, what you do is you draw the right triangle that includes the angle you just drew. Now, I could draw two right angles. I could draw this one and that one, but that doesn't include the angle I know. So I'm going to draw a right triangle here, coming out and going down like that. Like that. And this is how long? 440 kilometers. Now, you look at this, and this is B, right? So this is, let's look at B sub x. B sub x is the component along the x-axis. By inspection, is it plus or minus? It's this one up here. Is this positive or negative? It's positive. Let's hear it. It is positive. You write that down like I just did there. That means I thought about this and I decided it's positive. Then you write the hypotenuse. 440 kilometers. Then, looking at the triangle you drew, you label the three... Yes, ma'am?
So, when you decide which side is positive, which is negative, is this like the last chapter where you can choose it, or is it...
No, once I have chosen, to the right is positive, and up is positive. That was where I made my arbitrary choice. I could have chosen plus over here and negative up there. But once I have chosen these coordinates, that arrow is that portion of that vector pointing in the plus x direction or the minus x direction. You tell me. Is this arrow right here pointing in the plus direction or the minus direction? So that's where that came from. Now we're not done. You have to label the three sides of that triangle: opposite, adjacent, and hypotenuse. Hypotenuse is easy. You write the hypotenuse, but when we look at these sides, this side is the adjacent side, and this side is the opposite side. The opposite side is across from the angle. The adjacent side is next to it. Adjacent, if you go to SOHCAHTOA, adjacent always goes with which trig function? Sine or cosine? Cosine, good man. Cosine, 45 degrees. And if you multiply that out, you get 311 plus 311 kilometers. Now, what about the y component? Is the y component over here going in the positive or negative y direction? It's pointing down. It's below. So this vector has a positive x component by inspection and a negative y component. Negative. We write, again, the hypotenuse. And since we already used cosine, what do we have to use? Come on. Sine. You cannot use the same trig function for both the x and y components. If you get one of them right, you know what the other one's got to be. This turns out to be negative 311 kilometers. So we can summarize that. Going 45 degrees southeast, a distance of 440 kilometers, is equivalent to going east 311 kilometers and then going south 311 kilometers. That's what we're saying here. So this is equivalent to plus 311 kilometers in the x direction, followed by minus 311 kilometers in the y direction. By the way, is there any way you can sort of check these? Yes. Go ahead. Go ahead.
I had a question.
Yes.
So if it says southeast and it has a 45-degree angle, is it always going to end up...
Southeast is always 45 degrees.
Yeah. Well, is it always going to be a mirror of positive 311 and negative 311, but with like a different...
If it's southeast, yeah.
Okay.
Yeah, if it's southeast.
So one's going to be positive, one's going to be negative.
One can be positive. In fact, you tell me. Over, first name again?
Colby.
Colby. Over here. By inspection, if a vector was over here, what sign would the y coordinate be?
Positive.
And the x coordinate?
And negative.
Yes, down here. The y component would be,
Negative.
and the x component?
Positive. Or negative.
Negative. Up here, both are plus. Here, the x is positive, the y is minus. That's why you draw the diagram.
Okay, but the numbers are going to be the same
the hypotenuse, we mean the numbers,
Like the answer of the number, like 311. See how the answer is 311, like plus.
yes, that's 440 times cosine, or 400. Oh, that's because the sine of 45 degrees is the same as the cosine of 45 degrees.
Yeah.
That's the only case where it occurs. Also, northeast, southwest, and so forth. Okay? Let's read. I got 5 minutes left. Excellent point. No, unless it's 45 degrees, they'll be the same in absolute value. What about the last one? 550 kilometers, 53 degrees south of west. Now we got to be careful here. South of west, 53 degrees. That means west is here, south of west, we come down here like that, and this is 53 degrees. And this is how much? 550 kilometers. Is south of west the same as west of south? No. No. If it said west of south, you'd come up here. Different direction. So be careful. By inspection, let's write this. We have CX and CY. By inspection. Are these both negative, both positive? What do we got going on here? The x component, is it plus or minus? Now watch. If I complete the triangle, including the angle I'm given, make a right triangle here, like that. Which side is this? Adjacent or opposite? This is adjacent, and this is opposite. But this one is the x component. Is it positive or negative? It is negative by inspection. We write the hypotenuse. This is the adjacent side. Adjacent goes with cosine of 53 degrees. And we get negative, let's see, 331 kilometers. That's just negative 331 kilometers. And CY is CY, positive or negative? Negative by inspection. 550 kilometers. It's got to be the sine of 53 degrees. And that gives us negative 439 kilometers. So let's summarize that. See, you have to do more work to add or subtract the vectors. Now there are the components of each of those three vectors. If there were 4 vectors, if there were another leg in the journey, what would you have? Another diagram and another set of x and y coordinates. If you had 10 vectors, you'd have 1, 2, 3, you'd have 10 of these things. Now what do you do? Once, I'm going to take these off. Once you have all of the components of the vectors, the x component of the result is the sum of the x components. So on this one, you went 620 kilometers to the east. On this one, you effectively went an additional 311 kilometers. But on this one, you effectively went back 331 kilometers. You put a negative sign in there. So when we say add, we mean add algebraically. So it up on the calculator, we get 600 kilometers. So if you think about what we did as far as east and west goes, in this one we went to the right 620 kilometers. Here we went another 311, and then here we went back 331. For the y component, 0. Dr. Ladder, why did I write 0 in there? I don't have to do that mathematically. Why did I write 0? Why do I want you to write 0? To remind yourself that you calculated this and it did turn out to be 0. You thought about this. So on this first leg, we didn't go north or south at all. On the second leg, we went also south 311 kilometers. And on this third leg, we went south another 439 kilometers. So in the end, we did a total south of a negative 750 kilometers. Any questions? Now we're not done. We ain't done yet. Technically, that's the answer. The resulting trip is the same as if you went 600 kilometers east and 750 kilometers south. But now I want you to say, how far am I from home and what direction would I have to fly straight from home to get there? In other words, if I summarize this now, we're not done, you need to make another diagram. I'll summarize this. The resulting vector is 600 kilometers in the x direction and negative 750 kilometers in the y direction. Next and final step is draw the x and y components of the resulting vector. So we go 600 kilometers this way, and then we have to go 750 kilometers this way. So I made that a little bit longer. And I didn't draw that really well, so. How come I didn't put a negative on that? Because that is the length of that side of that triangle. The downward pointing arrow indicates the negative sign. So how do I find the hypotenuse and the angle? Well, I draw the hypotenuse, and I'm going to call this angle phi. See, by drawing that diagram, I'm telling whoever's looking at this that the angle that I come up with is south of east. So how do I find the magnitude of this? Whose theorem do I use? Pythagoras. So the resultant is the square root of 600 kilometers, now watch this, all squared. This is not 600 kilometers squared. Those are not the same thing. Those do not equal each other. It's 600 kilometers all squared plus, and because I'm going to square this, I do not put in the negative sign. Negative 1 squared is 1. So I just put in the 750 kilometers squared. Get your calculators and do it. All I do in my calculator is I do 600 squared plus 750 squared equals shift square root. I got 960 or something like that, rounding it. So there's how far from home I am. And labeling this is the opposite, this is the adjacent. I use the fact that the tangent of the angle that I have drawn is the opposite over the adjacent is 750 kilometers divided by 600 kilometers. Notice I do not have any negative signs in here because these are the lengths of the side of the triangle. What happens to the kilometers? They cancel. You cannot take the cosine or the sine or the tangent of something with units. You must have unitless number to take the tangent of that, okay? So that turns out to be, it says that the tangent of the angle, do they actually do the intermediate step here? Yes, is 1.25, or I better be, yeah, 1.25. And how do you solve this? You take the inverse tangent, not the reciprocal tangent, that's different. You take the tangent inverse of both sides. The tangent inverse of the tangent is the angle, and this is the tangent inverse of 1.25, which means you take 1.25 and you use shift or second function or whatever it is. So do it on your calculator. 1.25 shift 10. I got 51.3. Anybody else? Don't trust me. Or negative or 51 degrees. Now the book shows negative 51 degrees. Okay? I don't like that. My diagram says that it's 51.3 degrees below the plus axis. And that's why I don't have a negative sign there. This shows me, if I said I got to fly a helicopter to pick you up, this tells me to fly 51.3 degrees south of east to find you, not up here. The combination of the angle and the diagram showing what the angle is the most clean way of giving the answer. Now, even in standard rescues are normally measured from north, so that's another whole thing altogether. Questions or comments? You have to be able to do this. You have to be able to do this. All right, we've got enough time here to start talking about projectile motion. In the previous chapter, we did constant acceleration motion. Also, zero acceleration motion, because it's zero means if the acceleration stays zero, that's constant acceleration too. But now we have something remarkable. We are going to make the transition from one-dimensional motion to two-dimensional motion. The motion of something flying through the air, not just up and down. This is one-dimensional motion. Now we're going to add, the sideways motion to it. Okay? How do we deal with that? Well, book doesn't really mention this, but I'm part cosmologist. It is a remarkable feature of space. You don't think of space as being anything, but there are physicists who study space. I don't mean outer space, I mean this stuff right here without the air in it. Turns out space is pretty complicated. But let me ask this simple question. In next week's lab, we're going to see that if you drop something about a meter, 1 meter, that's about a meter, isn't it? Yeah. And you time it with an electronic timer, it takes about 0.45 seconds to fall from rest. Now, of course, if I throw it down or throw it upwards, that changes it. But to just let go, it takes about 45/100ths of a second, a little under half a second. If I get on a plane for Bermuda, oh, wouldn't that be nice? Okay. Bermuda would be great. Okay. Or the Bahamas. I don't know. Anyway, blow me out of here, right? And that plane is flying good and clean, and that plane is not accelerated. That plane is flying so smooth I could actually sleep on it. And I wake up, and you ever, anybody flown like that when you wake up, you're not sure where you're at? It's like, whoa, 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 whoa. Or you've woken up in a hotel and you're not sure where you're at. But if I get up on that plane, and I drop this a height of 1 meter, how long will it take? Don't make it hard. How long will it take? Will it be different than the 45/100ths of a second that I get right now? Well, let me ask this. Are we actually sitting still? Isn't the Earth going around the sun? The Earth is going around the sun at 67,000 miles an hour. That's hauling ass. Does that affect how long it takes us to fall? No. No. What we find about space is what is occurring in one dimension, back, forward, up, down, left, right, is not affected inherently by what is going on in the other directions. Now there might be a physical coupling, but space itself says no. So if I skateboard on a skateboard at constant speed, okay, at constant speed. So the skateboard is not accelerated, and I drop this down 1 meter onto the skateboard, it will still take exactly 45/100ths of a second. The horizontal motion doesn't affect the vertical motion and vice versa. This is incredibly important. It means that when you have a multiple dimensional problem that you have to solve, you treat it as 3 or 2 separate one-dimensional problems. You just have 2 or 3 times as much work to do. We're not going to go to 3 dimensions, we'll go to 2. This is a 2-dimensional problem. It's going up and down while it is going left and right, okay? So we have to do a solution to the horizontal part of the problem and a solution to the vertical part of the problem, which we have already dealt with in Chapter 2. We dealt with free fall motion. So what about the horizontal motion? Well, now that we got vectors here, what did we say was the acceleration due to gravity? What is its direction? I heard it. Down. And down means damn down. Straight down. In fact, down is defined as the direction of the acceleration due to gravity. Is down the same everywhere on the Earth? Is down in China the same direction as down here? The hell it is. Here's the Earth, here's me, and here's someone in China. Down is this way in China and down is that way where we're at. They're different. Down is not the same everywhere on the Earth. Down means towards the center of the Earth. So be careful about that. Down is different on different places on the surface of the Earth. It depends on where you are at. Okay? So don't fall into that trap. Down is always towards the center of the Earth. So, technically speaking, we get into an argument over beer or whatever. Boy, I need a beer. Yeah, it's my wedding anniversary. Is down right here technically exactly the same as down over here? No, it's a little bit different. But is it measurably different? No. Even over a football field, it's not measurably different. But if you are in the Navy and you lob a shell 27 miles to a target, over 27 miles, that could become important. All right. The acceleration due to gravity. Now notice the difference. Now it's got a vector over it. So I'm going to draw that baby. Okay? What I want to get at is, what is the x component of that vector? If this is x, and y could be up or down, doesn't make any difference. What is the x component of that vector? 0. 0. When an object is only under the influence of gravity, it is accelerated with constant acceleration of 9.8 meters per second squared down, but horizontally, the acceleration is 0. It is 0. There's no acceleration horizontally. So when I throw this, if you look at the velocity of this thing, first of all, does it follow a straight line? Does it move in a straight line? Don't make this hard. No. If I throw it really fast, does it go in a straight line? Be careful. No. No. Does a bullet go in a straight line? No. A bullet falls. You shoot a bullet this way straight out, it falls while it's going out. And the fall can be enough for you to miss your target. So anybody who's a marksman knows that a rifle sight is calibrated for specific distances. But horizontally, the acceleration is 0. And that means that when you project an object upwards, and one of the first things we'll do here is, if we project it upwards with some initial speed and some angle, there's an initial x velocity and an initial y velocity. This is the first thing you do in these problems, is when an object is thrown, what angle is it thrown and how fast is it thrown? That's the polar form of the initial velocity. What's the speed and direction that it's shot out at? But horizontally, the acceleration in the horizontal direction is 0, because gravity is straight down. Therefore, if I start writing out those constant acceleration equations, what I get is v final is v initial x. The final x velocity doesn't change. There's a plus ax times t, but this is 0. So we get this. The horizontal motion is motion of constant velocity. Now we're ignoring air resistance, okay? No air resistance. All right? Also, we would have that x final is equal to v initial is x initial plus v initial times t. There's no 1/2 at squared. Notice, I have to be careful. This is the initial x component of the velocity. If you go home and you watch, you can go on YouTube and watch, look up the B-52 bomber, the B-29 or something like that in World War II. You see these planes going along at hundreds of miles an hour, and they're dropping bombs. How horrible is that? We've never had to experience bombardment like that from upstairs. In London, they had bombs falling on them. We've never had that in this country, but we're spoiled. But if you watch the plane, and the plane is being filmed from another plane, you see these bombs, it's as if the plane is just sitting still and the bombs are falling straight down below the plane. The bomb leaves the plane, the bomb doesn't do this, the bombs fall straight down going with the plane. So does that mean that the bomb hits the ground that's right under the plane when it's dropped? No. It hits ahead. Question?
Isn't that kind of like the same idea as if like you jump on top of the plane or on top of the train as if
Yes.
in a cart?
Yes. You know, they show these guys on a train wrestling on top of the train. If it's flat up there, the train, if there's no wind, and if the train is not speeding up or slowing down, they might as well be sitting still. It's not hard. And if you can juggle, okay, and you walk at constant speed, it's just as easy as standing still. Now, if you change your speed, that's totally different. Okay? Because the balls, if I do this, I throw it up, it comes right back down. I don't even have to watch it. I just throw it up, it comes, you know, as far as I'm concerned, it comes right back into my hand. I don't have to, unless I am changing my velocity. And then this is not zero. So the first feature of free fall motion, or projectile motion, this is where we'll stop, is that the horizontal portion of the motion is motion with zero acceleration, constant velocity. Now let me assign some homework problems here. I've already assigned some, right? I went up to 8. I went up to 6. Okay, let's do 8 and let's just do 8 and 9. So 3-8, 3-9. So for you folks, they'll be due, what will they be due? I guess Wednesday. And for the folks that are watching on video, they'll be due on Friday. Okay, one final thing. When you go out this weekend, we all need a break. God knows we need a break. You are supposed to continue to socially distance, wear your mask, and behave properly even when you're not on campus. If you're out among other people and you're closer than 6 feet, you need to wear a mask and you must cover your nose. If you don't cover your nose, you might as well not be wearing the mask. All right? If you don't do that, someone's going to get sick, we'll have a spike here, and then the whole live teaching will be shot. So pay attention to it, okay? All right. Have a great weekend.